Swayam Prabha. Digital India. Educated India.
Welcome to Fundamentals of Nano and Quantum Photonics. I am Naresh Imani. I am a faculty member in the Department of Electrical Engineering at IIT Hyderabad. I hope you had a chance to take a look at the introductory video that we had uploaded to the website. So wherein we talked about what this course is about. So this is the first week of the course, and so let's get started. So I have shown this image in the introductory video wherein we emphasize the size mismatch between the electrical and optical components. So in the center you have the electronic IC, which probably has millions of transistors. So many transistors can be integrated in a very small dimension, whereas the optical devices are much larger in size. This is what we emphasized in the introduction. So I want to highlight this once more. So essentially, if you look at the graph on the right, you see on the x-axis the critical dimension, the sizes of the devices. On the y-axis you see the operating speed. If you look at the semiconductor electronics, which is the reason why the current technology has progressed so much, we see that the electronics is essentially deep submicron. The dimensions of the MOSFETs are much below 1 micron. So we call it deep submicron. And the operating speeds are typically around few gigahertz. That's the maximum speed that you can achieve. So the electronics operate in this section of the graph, whereas optics is much larger. The devices are much larger. I mentioned the optical fiber, which has a core diameter of about 10 microns. So the optical devices are much larger, but their operating speeds are also much higher because we are dealing with the frequency of light, which is in the range of hundreds of terahertz. So it is natural for us to want the best of the both worlds. We want the small dimension of electronics, and we want the fast operating speeds of photonics or optics. So that quest is what leads us to nanophotonics. Nanophotonics I can broadly define as the science of light-matter interaction at the deep subwavelength scale. Why are we interested in this light-matter interaction? Because we want to miniaturize the optical devices and also bring about various new functionalities which are probably not possible with macro-scale devices, macro-scale optical devices. So this is the idea of nanophotonics. So how do we understand this, right? If we look at nanophotonics, the field itself, it's relatively new. People have been talking about nanophotonics in the last 20 years. But if you look at the examples, I mean, in the past, long in the Roman era itself, there were some devices that were made which use the principles of nanophotonics. Of course, at that time they didn't understand what they were. So here are some examples. On the left, you see what is known as a Lycurgus cup. So this was a artifact made in the Roman era in the 4th century, around that time. So they had a metal structure, and in that they had some glass matrix. So this is a cup that they made. If the interesting feature is that if you look at the cup in the transmission, you see the pinkish coloration that is coming in. But if you shine light from the front and look at the reflection of the cup, it is greenish. So why does this come about? Probably or definitely they didn't understand why this was happening, but this was due to the fact that during the fabrication of the glass, some small amounts of gold and silver got mixed in the range of few parts per million. That very small concentration of gold and silver, when mixed during the formation of glass, can lead to dispersion of very small nanoparticles, which actually can give these interesting properties. Okay, as I said, they didn't understand it in the 4th century, but by the time we came to the medieval era, in the Europe, you see that there are a lot of these churches built with stained glass windows. The bottom image is an example of that. This is probably Notre Dame. I'm not very sure though. So you see this is beautiful colors that are coming about. Again, these are all glass which is colored. But by the time we come to medieval Europe, the artisans understood how to make these colored glasses precisely. So they would introduce controlled concentrations of various metals and then get these colors. And the interesting feature is that even though these stained windows are done, are fabricated probably a few centuries back, 3 or 4 centuries back, they still look very bright. If I look at my shirt, if I wear it for a couple of years, it gets faded, but these colors are not faded. The reason is this is what we call as structural colors. It's not because of a dye that is mixed, but it's because of structural colors, and there are some important applications for these things. Okay, again, the stained glasses are all brought about by introducing nanoparticles in glass. So this was the example from Europe, and more recently, if you look at the work of J.C. Bose in Calcutta at the turn of the century, he did some interesting work. You might remember that Heinrich Hertz demonstrated electromagnetic waves in 1880, 87 or 88, that time frame. So, and Bose in 1890s, he did a lot of interesting experiments. He created a source of electromagnetic waves, and then he tried to transmit them. In fact, he showed some experiments wherein he was able to transmit millimeter waves over a range of couple of kilometers. So in this particular example here, you see this was actual image of an apparatus used by Bose, and he had a transmitter of electromagnetic waves, and then there were these wires you see in the front. These are essentially used to polarize electromagnetic radiation, and if you compare the diameter of the wire to the size of to the wavelength, it is definitely deep submicron or sub-wavelength rather. So there are some of these examples where a lot of interesting things can be achieved by using nanoscale structures, or structures which are much smaller in dimension compared to the wavelength. And these are the artificial, or rather man-made examples. If you look at the nature itself, there are some interesting light matter interaction that happens. The image on the left is the top images are of the microscope, or the photographs of butterflies. You see butterflies have these bright nice colors. How do these colors come about? If you take a butterfly wing and put it under a microscope, you would see something you increasingly magnify it. So as you go to smaller and smaller dimensions, you will see that there is some nice structure that is coming about. But beyond a certain point, you cannot resolve structure in a traditional microscope, because what we have, there is something called as a diffraction limit, which prevents us from actually clearly imaging at very, very small dimensions. We'll talk about it later in the lectures today. So if you go to what is known as SEM, it can help us resolve these very, very small features. And the bottom 4 images are the SEM images of the same butterfly wing. And you see that as you go to micron and nanoscale dimensions, there is this beautiful structure, the periodic arrangement of material that is coming about. And because of this periodic arrangement of materials, the butterfly gets its color. The butterfly wings get the color. So this is a very interesting thing. Why does this happen? Just because there is a certain pattern, why should it give color? All of you might have seen the CD discs or DVDs. If you look at them, at an angle, you'll see that there is some color cut that's coming about. Why does that happen, right? Or a more common example, you might have seen a small drop of oil that is on a road. If you'll see that a thin film of oil will cause colors to come about. If there is sun and then the sunlight is reflected from it, there is just different colors that are coming about. Why does this happen? All of this is essentially light matter interaction. Okay, and I hope that by the end of this course, you will understand how to interpret it. We see there's a lot of beautiful things that are going around, and this course I hope will help you understand some of that. And when we talk of light matter interaction, we'll have to start at the beginning, that is the Maxwell's equations. I'm not going to tell a lot of things about it. I'll assume that you're already familiar with that. But briefly, Maxwell's equations in the modern form are given by these 4 equations, wherein you have the Coulomb's law, which essentially tells you what is the electric field when you have free charge, right? You can calculate the electric field for any distribution of charges using Coulomb's law. And then there is Faraday's law, which tells you how if there is a change in magnetic field, what is the induced current. So Faraday's law tells you that. And then there is Ampere's law, which tells you how the magnetic field is produced when you have changing current. Ampere's law. Right? These were laws that were already known at the time of Maxwell, but he kind of combined all of that into a systematic formalism, and he came up with these 4 equations. And these are essentially fundamental to everything around us. I just want to emphasize this. I like this quote of Richard Feynman, who said that if from a long view of history of mankind, seen from say 10,000 years from now, there will be little doubt that the most significant event of the 19th century was judged as Maxwell's discovery of laws of electrodynamics. The American Civil War will pale into provincial insignificance in comparison to this important scientific event of the same decade. The idea is that these are fundamental to everything that is going on around us. And there's an inherent beauty to it. We say that Maxwell's equations are scale invariant. So the Maxwell's equations can be applied to, let's say, megahertz, kilohertz, gigahertz, terahertz. It doesn't matter what frequency of waves you're dealing with. You apply the same set of equations. Okay. And these are very useful. So I would, you should really pay attention to them. Okay. So we have Maxwell's equations, but what next? There are these various terms: magnetic field, electric field, and flux densities, and so on. So you'll have to understand what those exactly mean and how to compute them. I would assume that you have done that in the basic electromagnetic courses. So I would like to just emphasize what we call as constitutive relations here. So the constitutive relations tell you how the flux density changes as a function of field. Okay. So there are 2 of these flux densities. The first one is the electric flux density, which is denoted by D. Okay. What this tells you is what happens when electric field is incident on a material. Okay. So for example, let's take a piece of glass. When that is put in electric field, what happens? Okay. So you would expect that the electric field has this, the field lines, which will cause the charges to move. So because of this electric field, the charges in the glass will move to the positive, the positive and the negative charges will separate, as I'm showing schematically here. So this separation of charges is known as polarization. Okay. So when this, wait a minute, you might say that where are the charges in glass, right? Glass we know is insulator. It doesn't have charges, right? How does this charges come about? So to understand that, we'll have to make a distinction between free charges and bound charges. Okay. We will again go into the details of it maybe, in the next week a little bit more, we will talk about it. But for now, yeah, even if you have insulators, there is this electron which is bound to the nucleus. And when you apply an electric field, there will be a slight displacement of the electron related to the nucleus. And that small displacement, when they are adding up in a material, eventually lead to charges at the edges, shown in this fashion. Okay. This is for linear distribution of polarization, or rather constant polarization. Okay. So what happens is the D displacement flux density will no longer be, it is given by epsilon naught E, and then the polarization which is contributing to it. Okay. So if I have vacuum, of course the polarization term is going to be 0. So what is this epsilon naught? Well, epsilon naught is the permittivity of free space, right? We know this from our 12th standard. Epsilon naught is permittivity of free space, which is about 8.85 into 10 power minus 12 farad per meter, right? And the polarization, it is proportional to electric field for now. So the polarization will be given by epsilon naught chi times E, right? So this chi is what we call a susceptibility, right? And then if you substitute back, you'll see that the D term is going to, if you substitute back the susceptibility, you will see that D is going to be epsilon naught 1 plus chi times E, and this 1 plus chi is known as relative permittivity. Okay, it is going to change from material to material. For example, if I take silicon, the permittivity is going to be 11.9. If I take silicon dioxide, the permittivity is going to be 2.25, and so on. So this will be material dependent. So this is how various materials respond. So to capture that, we use the constitutive relations, right? Similarly, similar to the flux density, electric flux density, we have the magnetic flux density, which is given by the term B. So the B will be given by mu naught H. H is the magnetic field. Sorry. magnetic field, and B is the flux density. So in addition to the magnetic field contribution, you will have the response of the material. For example, if you take a ferrite material, it will have polarization, magnetic polarization that can occur, and that is represented by M. And because of that, you can combine that can be captured in terms of a relative permeability. Relative permeability. And of course, mu naught is the permeability of free space. So mu naught is going to be 4 pi into 10 power minus 7 Henry per meter. And relative permeability is a constant. It doesn't have dimensions. Even relative permittivity doesn't have any dimensions. It's a number, right? So in this course, we will really not focus on magnetic materials. So it turns out that magnetic materials, the magnetic response is actually quite hard in optical frequencies. Okay, so a lot of we will only focus on materials with M equal to 0. So they don't have any magnetic polarization. So because of that, for rest of the course, we will use mu naught B is equal to mu naught H, right? That's a simplification that we will follow. In fact, if you want to actually engineer a magnetic response, we'll have to go to some additional, great lengths to make it happen. And we will talk about it maybe, in the week 4 or so, in the context of metamaterials. All right. So this is about the matter. So nanophotonics essentially is solving Maxwell's equations in various medium. For example, let's say I have a hypothetical structure consisting of material with various permittivities arranged in some shape. There is some periodic arrangement, there is some random distribution, and there's a host permittivity. So if I have this distribution of permittivity, how do I solve Maxwell's equation? Well, this is a normal problem wherein you can solve for the response. But what is more interesting for us is the inverse problem, wherein we want to achieve a desired functionality, and to achieve that functionality, what should I do? What should what sort of material should I use? What sort of geometry should I use? For example, I have a beam of light that is going, a laser pointer, right? I want to bend it at angle of 30 degrees. What should I do, right? Or I want to create a structure which will essentially, let's say, image. I want to create a lens, okay? I want to make a very thin lens. How should I have the distribution of permittivity to achieve that? Or I want to separate the polarizations. I have a beam of light. I want the S polarization to go in one direction, the P polarization to go in another direction. How do I engineer that? All of this. So, okay. So this is the core scientific problem that nanophotonics addresses. All right. So we will talk some more details in the subsequent lectures. For now, I will stop here. And if you have any questions, I'll be able to answer. If not, we'll meet in the next lecture. Thank you so much.